Hey guys, today we want to derive the angular momentum expression for the rigid body, total angular momentum. And since we're talking about the momentum or angular momentum, we should probably start the derivation with the general definition of the angular momentum, just for any, let's say one single particle, which is actually position vector r crossed with its linear momentum. And expressed in the in terms of the position vector, this is simply r cross m r dot. So now we want to actually figure out the linear momentum in terms of the position vector capital R of the center of mass, because we can think of that object as if its whole mass would be concentrated on the center of mass. And then the motion can be described as the motion of a single particle, basically. Let's start expressing this general vector r, or in our case it's r sub alpha in terms of the capital R. And so this will be then r sub alpha capital R plus r alpha prime. For each mass element m sub alpha, this is actually the same. And then to get the total angular momentum, we would sum over all of these particles of mass and get the expression. So once we get the expression, we can substitute the r sub alpha into the expression for the summation, like sum of the all smaller momenta, and distribute the cross product and the sums to make our derivation a bit simpler. So let's distribute again. The distribution gives us 4 terms, and each of these terms can be simplified further. But to do that, we would need to recall some of the cross product rules, properties. One would be the distributive property, which is very important to understand, works both ways. I had some trouble understanding this, and as a result I spent 2 hours figuring out how to simplify those cross products. And so another property would also be a scalar property. So first, the distributive property, again, it works both ways. And also the property that concerns the scalar multiplication. Okay, so now we are ready to simplify each of the terms separately, and starting with the term 1, we can do the following. It helped me really to understand the process a bit better if I just undid the sum into its components. So I was able to see it better. So here, this capital R vector is not dependent on the alpha index, so we can take it out based on the distributive property, and then simplify the first term pretty easily to just stuff dependent on the center of mass alone. So the second term is a bit more involved, not too much actually, because once you figure out how to use the distributive property of the cross product properly, it becomes easier. So here the important thing to recognize is that also r dot is not dependent on alpha, but also each of little m's, m1 and 2 are scalars actually, so they can be also brought forward. So we can rearrange it like this and then apply the distributive property. So we can now then take the r dot out separately, combine the sum of the mass and position vector products to get this expression. But this is 0, because recall the problem 10.1 video I did earlier. we showed that this is actually 0. So for this third term, we have also a cross product of the position vector of the center of mass and m sub alpha r prime sub alpha dot. But the original m sub alpha r sub alpha prime was actually 0. I'm sorry, I missed the prime actually here. Okay. So since that's 0, the third term simplifies to 0. And the fourth term is also very easy. There is nothing to simplify because everything depends on alpha here. We can't simplify it any further. And so if we put it all together, we get the expression for the angular momentum. And then also we can use the, again, original definition of the angular momentum to say actually that the angular momentum of the total system of a rotating and moving in space rigid body is actually an angular momentum of that body relative to the center of mass and the motion of center of mass itself. And yeah, so this is it. Thanks for watching, guys.